Almost forgot. All right, so good morning, officially. Test number 2 is on Tuesday, November 17th. Okay, remember that. Same format as last time, so I'll post the PDF and then you work through it and then you upload your work on Gradescope, and should be good to go. Let's see here. Okie dokie, okie dokie. For a quick kind of review, what did we do? Oh yeah, we were graphing quadratic functions, so parabolas, right, pointing up or down. We're actually gonna kick it up a notch today and graph rational functions, which is a polynomial over a polynomial, so a little bit harder, right? But so we talked about quadratics, and then we got into, oh yeah, the end behavior of polynomials, so that's gonna come in handy for us. Right, and then long division of polynomials, okay, which we're going to keep doing a couple of examples today, and just so we kind of really solidify things. And there are 2 ways that we can write a polynomial, right? We can write it as the quotient plus the remainder over the divisor, right? Or the divisor times the quotient plus the remainder. Notice that these are just equivalent, right? All I've done is I've multiplied both sides by d of x to move this d of x over here, right? So just, I'll copy this one into our notes today. So for review, right, we did polynomial long division, and the factor and remainder theorem, mainly the remainder theorem. Remainder theorem says that if you have, and now I don't have those notes are here. Just grab them. The remainder theorem says that if you have, I'm all over the map today. If p of x is divided by x minus c, okay, then r of x, the remainder, okay, is going to be the same as p evaluated at c. Okay, so that's what the remainder theorem says. And the factor theorem says that if you have p of x over x minus c, c is a 0. Oops, that CIS. C is a 0, okay, if and only if the remainder is 0. So this means an x-intercept when I say 0, right? So C is a 0 if and only if x minus c is a factor, which means that the remainder of this thing is 0. Okay. So that's what the factor theorem says. We're going to focus on the remainder theorem because it's a quick way of, okay, if we can divide this polynomial p of x, it might be easier to just look at what the remainder is, and then we would also know what this thing is evaluated at c, assuming that you're dividing by x minus c. So if you have x plus 1, your c would be -1, right? So you want to be careful there, but besides that, that's all that's going on here. Okay. Let me clean that up. Okay. So there are 2 ways that we can write these things out, right? Notice that if you have P of x over D of x is equal to Q of x plus R of x over D of x, right? The quotient plus the remainder over the divisor. The remainder is everything that's kind of left over, but you have to put it over the divisor because otherwise you're wrong. Just like when you do 5 divided by 2, right? That's 2.5. That's 2 plus 1 over 2, right? And so 5 divided by 2 is 2 plus 1 over 2. Okay, so same idea. If you multiply both sides by d of x, right? So if you do p of x over d of x, and then I guess I've been using this color, so times d of x is q of x plus r of x over d of x. I just want to show you that they are the same thing. Right? All I'm doing is I'm canceling d of x, and I'm moving it over here instead. But once I multiply this d of x in, what I get is I get p of x is q of x d of x plus r of x over d of x times d of x, which of course is going to cancel. So that's why p of x is q of x d of x plus r of x. All right, so that's how we went from here to here. They're the same. What you need to do is you need to find q of x and r of x, right? You need to find the quotient, which is in your long division, it's the number up top, and then the remainder is whatever is left over. So let's do a few examples. Focus your attention on that first page, those ones at the bottom there, and then you can easily do the factor theorem ones too. But so here, we've got lots to choose from. I feel like we did, I can't quite remember which ones we did or which one. X. Okay, this is the long example. So if you need a step-by-step example, there's a long one in there. We did 4 together. Yeah, and then I asked you to do as many of these as you can. And then we'll do some of these for review. So we've done 4 already. Okay. Is there anyone in particular that you want to go through? I'm definitely going to go through this one with you guys. And which ones are kind of similar? Maybe 11. Okay, so we'll do 11 and 14 as part of our sort of review. I guess we can kind of, let's say we end the review here. Call it fresh. Okay. So these are the same, it's just we're practicing putting them in different forms. Once you have q of x and r of x, it doesn't really matter which form you put it into. Sometimes it'll specify, as long as you pick one of these forms on the test, I'll tell you which form I want it in, right? Or I might just ask you, hey, what's the quotient, what's the remainder? Something like that, right? So our goal is to find q of x and r of x. So here we go. For 11, we had 2x minus 3 going into 2x to the 3 minus 3x squared minus 2x. Okay. Okay, good. First thing you have to do is you want to make sure that if you've got x to the 3, then it's followed by x squared and then x. And then if there are any kind of x's missing, so let's say there was, this term wasn't here, you would have to add plus 0x squared because you have to have the spacing correct. So we didn't get to that point, right, last day. So what I'm going to do, I'm going to make a note here. We need to make sure all powers of x are listed in order. Okay, the next one, I picked it for that reason, right? If you've got x to the power of 5, x to the power of 4, notice how there's no x to the power of 3 here. So what we're going to do is we're going to squeeze in plus 0 times x to the power of 3, and then same thing, plus 0 times x, just to have those placeholders, because otherwise our quotient gets mixed up. But we'll see that in the next example. So in this case, we're good. All right. Do you remember what we did? We need to take the leading term here and divide it by the leading term here. So on the side, or even in your head, you can do 2x to the 3 divided by 2x, putting you at x squared. Now I'll do it on the side here. 2x to the 3 divided by 2x puts me at x squared. And so that's what's going to go up above here. Then what I do is I kind of bring it back down. So x squared times 2x minus 3, I'll use a different color here. X squared times 2x minus 3 is going to be 2x to the 3 minus 3x squared. Okay. So that's going to go here. 2x to the 3 minus, hey, crazy, 3x squared. Yep, just making sure. The next thing I do is I need to subtract these things, right? Making sure that you subtract. So what's always going to happen is that these are going to go to 0, right? That's what we're forcing to happen here. So this is going to be, well, maybe I'll use 0. So 2x to the 3 minus 2x to the 3. Negative 3x squared plus 3x squared is also 0. Plus 0x squared. 0 is now our new kind of dividend. And then what I'm going to do is I'm going to bring down this negative 2x. So what I have to do here is now I'm kind of back to square 1. So now I look at the 0 and I take 2x, 0 divided by 2x is 0. So plus 0. And then, of course, 0 times 2x minus 3. Wow. Womp womp here. 0 divided by anything is 0. I'm stuck on which color to use here. So I guess 0. I guess I better write it out. 0 times 2x minus 3 is 0 minus 0. There. If I subtract these, well, 0 minus 0 is 0. Oops. Negative 2x minus negative 0, of course, is just negative 2x. So now I can deal with this one. So negative 2x divided by 2x. It's negative 1. Ooh. Okay. Then I take -1 times 2x minus 3. -2x plus 3. So then this goes here. -2x plus 3. If I subtract these, -2x plus 2x is, of course, 0. And then 0 minus +3, -3. So here, our quotient then, therefore, q of x, because now we're done, right? There's no more x's that we can, once we've finished with the highest power of x in the leading coefficient, or in the, sorry, the divisor, then we're done, right? So this is the remainder, this is the quotient. So q of x is x squared minus 1, and r of x is -3. Okay. So you can write it as either p of x is d of x, q of x plus r of x, right? And recall p of x is 2x to the 3 minus 3x squared minus 2x, and d of x was 2x minus 3. Okay. So we won't use the remainder theorem because it needs to be in the form of x minus c. And here we've got 2x minus 3. So we would need to rearrange this, but that's not the division that we've done. So we can't use the remainder theorem. It only applies for x minus c as the divisor. Let's do another one. Let's do this 14. It's huge. I'm going to copy it so I don't have to keep scrolling back and forth. Hey. There. Okay. Maybe I'll put it on a fresh page so I can have room to breathe. Okay. All right. So my divisor is 3x squared minus 3x plus 1, and it's going into 27 times x to the 5th minus 9x to the 4th plus 3x squared minus 3. So here, the first thing we need to do is we need to rewrite this, because we already talked about it, including all powers of x. So p of x is going to be 27x to the 5th minus 9x to the 4. There's no x to the 3, so I need to throw one in there, plus 0x to the 3. Notice that I'm not really adding anything. I'm adding 0. I'm allowed to do that. Plus 3x squared. And then same idea, I need another x here before I can just do the constant. So plus 0x minus 3. So this is your new dividend, right? So you need to have spaces for all of these powers of x, starting from the degree, right? So the highest power of x. So now we can do this division. It's going to be a biggie, but that's okay. 3x squared minus 3x plus 1 is going into this whole thing. Oops, 27, not just 7. 27x to the 5th minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. Okay. So I'm not going to do my work on the side, and that's okay, you don't have to. You can just do it in your head or on your calculator, right? But, or maybe I should, but I don't really have any space. That's the problem. I'll make a little bit of space here. But just like before, what we're gonna do is we're gonna start with this highest, or this leading term, right? 27x to the 5th, and divide it by the leading term here. Okay. I guess it's easier if I just do my work kind of on the side. 27x to the 5th divided by 3x squared is going to be 27 divided by 3. Use your calculator. I know you're probably better at math than I am. Oops. But you don't want to muck this up. X to the 5th over x squared is going to be, remember our exponent laws, right? So x to the 5 minus 2. And so you get times x to the power of 3. Okay. So here I have 9x to the power of 3. So now in my head, or kind of on the side on a scrap piece of paper, you're going to do 9x to the 3 times this divisor. Okay. Let's see here. How can I? All right. 9x to the 3 times 3x squared minus 3x plus 1 is going to be 27, of course. Oh yeah. Okay. 9x to the 3 times 3x squared is going to be 27x to the 5th, which is what we're forcing here. Right? Add, if you've got the same base, then you can add your exponents. 9x to the 3 minus 3x is minus 27x to the 4th. Oh, plus 9x to the 3. Okay. Now I'm going to put that in here. So I get 27x to the 5th minus 27x to the 4th plus 9x to the 3. And remember, we have to subtract these. This term is going to go away, just like we're forcing it to. Negative 9 plus 27. Notice this is why we had to stack our powers, right? Because we're going to get an x to the 3. So even if we didn't have one originally, we need to subtract the same powers, right? And so you get negative 9 plus 27 puts me at plus 18x to the 4th. 0 minus 9x to the 3 minus 9x to the 3. And then, I mean, technically it's plus 0 times all these powers. So 3x squared plus 3x squared plus 0x minus 3. Okay. Now we do the same thing with 18x to the 4 divided by 3x squared. 18x to the 4 divided by 3x squared is going to be 18 divided by 3 is 6x squared. So here you get 6x squared. 6x squared times the divisor. Oops. 6x squared times 33x squared minus 3x plus 1 is going to be 18x to the 4th minus 18x to the 3 plus 6x squared. 18x to the 4 minus 18x to the 3 plus 6x squared. All that's being subtracted. No wonder I got you to do these on your own. Otherwise, this wouldn't make sense at all. This makes 0. well, it might make some sense, should make some sense. Minus 9 plus 18 puts me at plus 9, but I'll just make sure. You do not want to mess this up. X to the 3. 3 minus 6 minus 3x squared plus 0x minus 3. Now I do the same thing, right? 9x to the 3 divided by 3x squared. Okay, I'm running out of room over here. 9x to the 3 divided by 3x squared. Luckily, we're almost done. 3x. Okay. So I get plus 3x. And then 3x times 3x squared minus 3x plus 1 is 9x to the 3 minus 9x squared plus 3x. Okay. 9x to the 3 minus 9x squared plus 3x. Subtract all of that. 0, of course. Negative 3 plus 9 puts me at plus 6x squared. 0x minus 3x puts me at negative 3x and then minus 3. Okay. This is our last one, right? Because here we've got an x squared and our highest power here is x squared. So I won't be able to divide by x squared anymore. So whatever we're left with at the end of this round, let's call it, is going to be our remainder. So here we go. We have 6x squared divided by 3x squared, which is going to be 2. So up here we have plus 2. Notice that we go from x to the 3, x squared, x, and then just a constant. And so this is going to be our quotient. And then we're going to find our remainder. 2 times 3x squared minus 3x plus 1 is 6x squared minus 6x plus 2. So 6x squared minus 6x plus 2. Subtract all of that. We get 0. Negative 3 plus 6 puts me at plus 3x. Negative 3 minus 2 puts me at minus 5. Therefore, q of x is going to be this 9x to the 3 plus 6x squared plus 3x plus 2. Oh, I need to keep it up here so I can copy it. 9x to the 3 plus 6x squared plus 3x plus 2. And the remainder is 3x minus 5. Once you have Q and R, then you can kind of set up the answer whichever way you want. Yeah. So this work on the side is not something that I need to see, right? You'll probably need to do it somewhere, unless you're some crazy math whiz, right? Even just to make sure. This is all that I need to see, right? And then finally this, right? Any questions about that one? No. Yeah. All right. Then let's go to section 3.6. 3.6 is on rational functions. And we're going to focus on graphing rational functions. We've already talked about rational functions. A rational function is a polynomial over a polynomial. So the The rational function is something like p of x over q of x, where p and q are polynomials. We'll bring this in here from our notes. And if you have a look at the notes, all I'm expecting you'll see why I say all in a little bit if you haven't read ahead. All I'm expecting you to do from this section is just graphing, right? Notice that it's just one page. It's chock-a-block full of information, but we're just gonna graph these rational functions. So given something like this, we're gonna sketch a graph, and of course we're gonna check our work in Desmos, right? And so we're gonna develop just the procedure for graphing anything like this. So a rational function is something with a polynomial over a polynomial, right? So we're gonna develop, how are we gonna do that? And then it's just a matter of practicing, but also being patient when you're working through these. And then, of course, check your work in Desmos. Okay, so let's talk about, so we'll establish some things here. These two are both polynomials. P of x and q of x are polynomials. Okay. Another thing that we're going to assume is that p of x and q of x have no factors in common. So it's been simplified with no factors in common. So I'll say it's simplified. Okay. We'll talk about the special case, or what happens when they do have factors in common. That's at the bottom of the page there. But for now, we're just going to assume that they have no factors in common. Okay. All right, so what do we have here? Well, first thing, if we just scroll down and have a peek at what we need to be able to do, well, so to graph these, it kind of holds our hand and says, you're going to find the intercepts, you're going to find the asymptotes. You've probably heard of asymptotes before, right? But asymptotes are some imaginary line where a graph comes up to it and it approaches it, but it never actually touches that asymptote. So we'll figure out how do we find these asymptotes. And then we're going to use these to sketch a graph and state the domain and range from the graph. And then, of course, use a graphing device to confirm your answer. It should be probably Desmos is the easiest. If you've got a TA83, you can do that too, but I don't expect you to, so just use Desmos. It's free. Okay, so intercepts are, we've already talked about intercepts, and the same idea applies as when we were doing quadratics, right? So intercepts are just on the x-axis and on the y-axis. So you need to figure out when y is 0, that's your x-intercept, and when x is 0, that's your y-intercept. So the intercepts we've already seen in a different way, but the logic still applies. The asymptotes are going to be the new part of this section. And then kind of sketching around these asymptotes can be a little bit of a drag. Okay. So let's talk about these asymptotes here. Oh, and I'll bring in that little side note here. Because notice, okay, so if we have a line at x equals a, so just some vertical line, we call that a vertical asymptote. And what happens as x goes to a from the right, what we're seeing here is that this function, or y, is going to go up towards positive infinity. From the right might be different from the behavior from the left. So to kind of signify that, we have a, and it's hard to see here, but a to the plus means we're coming in from the right, and a to the negative means we're coming in from the left. And the behavior, it could be, they could be going up together like this around the vertical asymptote, or they might be going like this. So there are a lot of different options. So that's why we have this here. X approaching a from the left, so a to the power of a negative. X approaches a from the left is how you're going to read that, and x approaches a from the right. And then, of course, x going to negative infinity, x going to positive infinity, which we've already seen. Okay, so I'll just make a note here. X going to a from the right, or from the positive side is the idea. And x going to a from the left, or from the negative side. A from the left. Okay. So these asymptotes, we need to figure out when do they happen. Okay, so that's what we'll talk about first. And then we need to be able to figure out, okay, well, what's the behavior of the function as we approach x from the right and x from the left. Same thing here. It could be going down either from the right or from the left. The idea is similar for a horizontal asymptote. So now you have this horizontal asymptote where y approaches the asymptote, as x goes to positive infinity here, So you can approach this horizontal asymptote as x goes to positive infinity or negative infinity. So these are as x goes to positive or negative infinity, you approach horizontal asymptotes. And same thing here, it kind of settles down onto the horizontal asymptote. It's never going to touch that horizontal asymptote. Okay. When do these things happen? Okay. That's what the next blurb is for. This one is going to be kind of one of your money makers for this section. So I'll highlight it here. You'll want to keep it handy. Okay. So if you have some rational expression, so you've got a polynomial and a polynomial, Notice here the leading terms are going to come into play later on, okay? And so the numerator has degree n, and the denominator has degree m. Numerator has degree n, and the denominator has degree m. Okay, so the first thing is the vertical asymptotes are the line x equals a, where a is the zero of the denominator. Okay, so wherever the denominator is equal to 0, those are your vertical asymptotes. Where the denominator equals 0. Remember, we can't divide by 0, and so that's why these things don't exist. So the asymptotes, if we see something like this, okay, Well, that means that dividing by, when x equals a, divides by 0, which is not allowed to happen. So here, it's kind of like a cutout from the graph, and so things are going to happen around that point. Okay? And so this is where the denominator is equal to 0, which means it's probably easiest if you factor the denominator and figure out where does this thing equal 0, right? What values of x make this 0? Okay. So here, notice that degree n and degree m come into play for horizontal asymptotes. And this is why I say, okay, probably best if you just have this thing handy somewhere. If n is less than m, okay, so if the degree in the numerator is less than the degree in the denominator, then this rational function has a horizontal asymptote at y equals 0. Okay? So at y equals 0, that's the x-axis. Then you might see some sort of horizontal asymptote depending on the behavior. The other option is if n is equal to m, right? Then what happens, so now you have the same degree in both your numerator and your denominator. Then you have a horizontal asymptote at an over bm. Notice an is the leading coefficient in the numerator over the leading coefficient of the denominator. And so we need to pay special attention, especially for these horizontal asymptotes, we need to pay attention to the leading terms, right? And if n is larger than m, right, which we had in the previous example, then R has no horizontal asymptote. Okay, so if we're taking something like what we just dealt with here, our leading term would be 27x to the 5th, right? And my leading term here is 36, I don't know where that came from, 3x squared. So now my n is 5 and my m is 2. 5 is larger than 2, so I'm not expecting any horizontal. A is confusing with A coefficients. I'm not sure. Oh, do you mean here that we're talking about as x goes to A and then the coefficients? Oh yeah, so we have to be careful, right? Because we use A kind of typically for the roots, but A subscript n is different from A subscript or A with no subscript. So A subscript n minus 1, A subscript 1, A subscript 0. So all these subscripts make them different from just A, x equals A. But yeah, it's confusing. But you can use C here as your coefficient if you want to. Yeah, next textbook. It's actually pretty common to use A's and B's, but you can use whatever you want. H and K. Yeah, good. But that is something to keep in mind, right? So if you're looking at this, then just remember that if it has a little subscript on it, it's going to be different from the A's that we're talking about here, these vertical asymptotes. Okay, good. So let's look at the one that we just did. Consider the rational function we just worked with. Grab it. it, oh, we had 27x to the 5th minus 9x to the 4 plus 3x squared minus 3, divided by 3x squared minus 3x plus 1. Okay, so here, what I want you to do is I want you to first look at the leading terms. Okay, so here, if you look at the leading terms, in this case, n is equal to 5 and m is equal to 2, right? N in this case is the degree of the numerator, right? And so here the degree of the numerator is 5 and the degree of the denominator is 2, which we're calling m. I'm only naming them n and m because we're referencing n and m here, right? And so so that's why I'm kind of making those connections. Okay. For the vertical asymptotes, right, then we need to figure out where this denominator is 0. So where does 3x squared minus 3x plus 1 equal 0? Okay. Maybe I'll put this over here. The vertical asymptote is where 3x squared minus 3x plus 1 is equal to 0. Okay, that's because we can't divide by 0, right? So any values of x, just like we've been pulling them out of the domain, so they're not in the domain, and that's true. And that's because they're acting as these asymptotes. And so what we need to do first is we need to figure out where is this thing equal to 0, right? And so we need to figure out where this is 0 because since we can't divide by 0, oops. Oops. Yeah. We can, I always just use the quadratic equation. And so here, this is a quadratic, 3x squared minus 3x plus 1 equals 0. Well, here I've got another a. You have to keep track of what these are. B is -1 and C is 1. Okay. So now I've got x is equal to -b plus minus the square root of b squared minus 4ac over 2a. Probably one you have memorized by now. Oh, yeah, thank you. B is -3. The other two are good. Thanks, Nara. All right, that would have been a mess. So -3 plus minus the square root of -3 squared minus 4 times 3 times 1 divided by 2 times 3. 3 plus minus 9 minus 4ac. Why am I stopping? So I'm getting a square root of a negative. Did I do something bad again? Or a C. Okay. What I'm gonna do, B is -3, yeah. And then A is 3. Oh, well, no, it's good. I'm gonna graph this to see if I'm crazy or what. 3x squared minus 3x plus 1. I think I'm crazy. 3x squared minus 3x plus 1. Oh, so it doesn't have any zeros. Bad example then, pulling from the previous section. I should have known better. So we're on the right track here. This is a negative divided by 6. Square root of a negative means we have no zeros. Okay. Which means we have no vertical asymptotes. Bad example. I should have pulled one from this section. But I wanted to make the connection between last section and this section. But anyways, we can talk about if there are any horizontal asymptotes, right? And so if we look at, so for the horizontal asymptotes, so therefore, no vertical asymptotes. For the horizontal asymptotes, and I'll just kind of highlight these. For the horizontal asymptotes, we have n equal to 5 and m equals 2. N equals 5 and m equals 2. So looking at our little summary blurb here, if 5 is, so if n is greater than m, then R has no horizontal asymptote. So kind of womp womp, there are no asymptotes. So since n equals 5 is larger than m equals 2, there are no horizontal asymptotes. Example. Let's pull one from this section. Oh yeah, got one on the side here. What if we have to graph r of x, I'm a rational function here, is 2x squared plus 7x minus 4 divided by x squared plus x minus 2. Yeah. Actually, I'm going to revise this and say find the asymptotes, not just graph it right away. We'll work up to that. Find the asymptotes of there. Okay. So first thing I'm going to do is I'm going to make sure these are written in order. They will be, right? So that's not something, but it is something that we should be checking. And so we've got 2x squared over x squared, which means my n is equal to my m. So already I know from here, if n is equal to m, then R has a horizontal asymptote at the numerator coefficient or leading coefficient over the denominator leading coefficient. Okay, but let's start with the vertical asymptotes. Okay. The vertical asymptote is where x squared plus x minus 2 equals 0. So however you want to do this, if you want to factor it, that's great. In fact, I think that's the easiest thing to do, either using the quadratic formula, which I prefer. So here, as you saw, A is 1, B is 1, C is -2. I'll try not to muck that up again. No guarantees. So then we have x is going to be -b plus minus the square root of b squared minus 4ac over 2a. X is -1 plus minus the root of 1 squared minus 4 times 1 times -2 over 2 times 1. This one works out. 1 plus 8 is 9. The square root of 9 is 3, so I'm going to jump to that. X is -1 plus minus 3 over 2. So x is going to be -1 plus 3, so 2 divided by 2, which is 1. And x is going to be -1 minus 3, so -4 divided by 2, which is -2. Okay. These are your vertical asymptotes. So you have an asymptote at x equals 1 and an asymptote at x equals 2. These are your vertical asymptotes. You can use these to write this out as a factored quadratic. So we can write x squared plus x minus 2 is the same as x minus 1 times x plus 2. We'll use that for later. Just make it a note for now. Okay, so what this is saying is that x equals 1 and x equals -2, we have these vertical asymptotes. So what we need to do is we need to figure out the behavior around these vertical asymptotes. We've done this before, right, where we took our number line and we picked test values around 1 and -2 in this case. But what you're going to want to do is you're going to pick test values really close on either side. So because we want to know how does it approach x equals 1 from the left and from the right, right? It might look something like this, or like this, right? Not like that. Like that. Right, so what we're going to do is we need to determine the behavior around x equals 1 and x equals -2. So we need to determine the behavior around x equals 1 and x equals -2. So what I do, and I encourage you to as well, is just kind of pick, so here's -2 and here's 1. Of course, on a number line, you want to make sure that what you're doing kind of makes sense on the number line. I'll put this up a bit. Pick values right close to -2 and 1. Okay. So pick test values close to the asymptotes. So here, for example, if I'm coming into -2 from the left, right? So here, I'm saying x is going to -2 from the left. Oops, not -1. From the left, right, is what's going on here. Maybe I'll write that a little bit clearer here. So x is going to -2 from the left. And then this test point, so that's this test point. This test point is as x approaches -2 from the right, right? I usually go down, but sometimes they go up. So here we're approaching x is 1 from the left, from this point, and here x is approaching 1 from the right. Okay. Same way that we were doing before when we were picking test points, we really only care about the sign because at these vertical asymptotes, it will go to infinity, so positive or negative infinity. So I'm going to pick a value to the left of -2. To the left of -2, I have, let's see here, let's pick -2.1. Right? Notice or remember negatives right there increasing as you move out this way. So try -2.1 in there in this original equation here. Copy. R of -2.1 is 2 times -2.1 squared plus 7 times -2.1 minus 4 divided by -2.1 squared plus -2.1 minus 2. So you can do this in your calculator, of course. 2.1 squared times 2 plus 7 times -2.1 minus 4. -9.88 divided by -2.1 squared minus 2.1 minus 2. So we get -9.88 divided, -9.88 divided by 0.31 is roughly -31.87. Okay. As I move closer, and you can try it with values that are even closer, right? -2.01, -2.0001, 0.00001. Right, as you approach -2 here, it's going to become a large negative number, right? And so here, I'll make this here. So what we found is that y is going towards negative infinity. Here. Okay. You can do the same thing, right? This is going to be easier. So what we had done before is we had factored. So we actually managed to factor the denominator. If we had just factored the numerator, it would have been a lot easier to find the signs, right? So that's what we're going to do eventually. But if you want to do it like this and you don't want to factor, then that's fine. You don't have to. You should just factor the denominator, but if you factor the numerator, it makes this easier. But we'll do that in our next example. But so what happens here, I'm not going to waste your time with plugging in values, but you can try values as they approach -2 from the right. So -1.9, 1.99, 1.999, 1.99999, right? And so you can plug in any one of those numbers, and what you would find is that it would go to positive infinity. Okay. Same thing here as you do x going to 1 from the left. 1 from the left, right here, you're at 0.9, 0.99, 0.999, right? Same idea. Trying any one of those values, and you would find that y is approaching negative infinity, and then finally y is approaching infinity. So here, we can already sketch this type of behavior, right? We haven't even dealt with the horizontal asymptotes, but in general, what we're expecting to see is a graph like this, like this, like this, like this, right? So here, this is gonna go kind of down, it's gonna go up, down, up, okay? We need to figure out the horizontal asymptotes before we can commit to anything. The horizontal asymptotes, where are they here? Right? Depend on the degree and potentially the coefficients of the leading terms. So the degree of the polynomial in our case, we said, okay, well, x squared divided by x squared. So n is 2 and m is 2. Okay. From the summary page, which I highlighted for a reason here, if 2 is equal to 2, which it is, then we have a horizontal asymptote at y equals an over bm. Okay. So what we're going to say is that for our horizontal asymptotes, since n equals 2 is equal to m equals 2, or n is equal to m if you want, we have a horizontal asymptote at an, or sorry, I should say y equals an over bm, which in our case is the leading coefficient of each of them, 2 over 1. So we have a horizontal asymptote at y equals 2. Okay. So at y equals 2, we have a horizontal asymptote. Now, what I want to do is let's just sketch this in Desmos to see what it looks like, right? And just to kind of get an idea of how these things behave. So where is my original equation? Let me just have it so I can put it into Desmos. We've got, now I'm going to put the numerator in brackets just so I can make sure that everything is being divided by the denominator. And so I've got 2x squared plus 7x minus 4, then divided by x squared plus x minus 2. Okay, so if you have a look here, what we found is the value of, and I'm going to try to, this is our horizontal asymptote, right? It looks like we're approaching y equals 2, which is right? And here we're approaching y equals 2. So we would need to figure out how does this function behave as x goes to negative infinity and as x goes to positive infinity, right? And then we also figured out what the behavior was around this vertical asymptote at -2. Well, we said it goes down and then it goes up, And then at the asymptote of x equals 1, we said that it's going to go down, and then here it's going to go up. So what you can do is you can just confirm these things by plugging in x equals, x equals -2. Looks like that's the asymptote. X equals 1. It's also an asymptote. And then finally at y equals 2, we had our horizontal asymptotes, right? So we managed to find all this information, and we didn't really find the behavior here, but we did this one, right? Where we just plug in values as we approach -2 from the left, and then here we would plug in values as we approach -2 from the right. Okay. But like I said, it's going to be easier if we factor that numerator and not just the denominator. Okay, so, but these are the core things that we need in order to graph this thing, right? The other things that we talked about are the x-intercepts and the y-intercept, right? There might not be a y-intercept necessarily, but often there is. So we need to be able to find the x and the y-intercepts. Okay. No, let's write that here. Just to kind of show that we're leaving that example behind. Because we were just supposed to find the asymptotes, we didn't actually need to graph them, but we'll come back to it. Recall the x and y intercepts the x-intercept is where y, or the function, is 0. Okay. One thing to keep in mind, right, if you've got a fraction that you're dealing with, that thing is only going to be 0 if the numerator is 0. Right? So a fraction is only 0 where the numerator is 0. Yeah. So that means you have to find the zeros of the numerator as well as the denominator. The denominator is for the vertical asymptotes, right? And so the easiest way to do that is to factor the numerator as well, like I've been saying, but I kind of didn't do it in the right order. That's okay. The y-intercept, we know, is where the x is 0, where x is 0. Okay. What I would do is, just to be safe, right, if you factored things, I would probably recommend using the original fraction, so the original polynomial over a polynomial that you've been given, just in case your factoring is wrong, right? So plug x equals 0 into the original equation to solve for y, right? Which is your y-intercept. So the x and y-intercepts we've already dealt with in the quadratic, but now we're applying that same, the logic still stands, right? Where, so the x-intercept is where y is 0 and the y-intercept is where x is 0. Which it might help if you remember the, just kind of here, these are x-intercepts and this is the y-intercept. This is where x is 0, this is where y is 0, right? So if you remember that, then you can remember how to find them. Okay. Let's talk about just the general steps for how do we graph things like this. Rational functions and their graphs. So sketching graphs of rational functions. Like we just established here, because you have to know for the x-intercepts, right? So our goals are to figure out where the intercepts are, what are the asymptotes, and what else do we need to know how to do here? Find the intercepts, the asymptotes, and then sketch a graph, and then state the domain and range from the graph. So that's easier. And then, of course, use Desmos to confirm. So we need to figure out how to find the intercepts and the asymptotes. So to do that, the easiest thing to do is to factor things out, right? You factor the numerator to figure out where the x-intercepts are, and you factor the numerator, or sorry, the denominator to figure out where the vertical asymptotes are. So with reference to 1, we factor the numerator to find the x-intercepts, and the denominator to find vertical asymptotes. Okay. So here, so that's why we start by just factoring the numerator and the denominator. So you're going to find the x-intercepts by determining the zeros of the numerator and the y-intercept from the value of the function at x equals 0. That's what we just talked about, right? Then, because you've already established what the vertical asymptote, or where the vertical asymptotes are, the next thing you're going to do is you're going to see what happens, right, with the y's. Are they going down to negative infinity, or are they going up around those points? And so what you're going to do is you're going to use test values. It's going to be a little bit easier if you have it factored already, right? The horizontal asymptote, right? I'll say see highlight above. So you use those horizontal asymptote rules that we highlighted. Where are they? Here. Right, so here we can figure out if we have a horizontal asymptote and what it might be. And it all depends on the degree of the numerator and the degree of the denominator. Okay. Then we can sketch the graph. Okay. You might find that you need additional points. You're always able to plug in points into the function and figure out, okay, if x is 4, y is going to be this. And so you'll be able to plot points. And technically, that's what Desmos is doing. That's what a graphing calculator does. It just evaluates the function at many points of x. So it's not actually drawing the whole line. It's drawing many points next to each other. So so it's just evaluating the function at many points. Tedious, but it is something that you can do if you find yourself stuck and you have to graph functions. But it's going to be really useful to know where are these asymptotes, where is the x-intercept and the y-intercept. And I'll admit some of these can be really tricky, but that's why you have to use Desmos to just kind of confirm what you've done. Do that. Okay. So, because, well, I guess, let's see here. So we already know what to expect from this one. So maybe what we'll do is we'll do a new one, and the ones I've got here kind of ready and loaded aren't that. Nope, it's okay. Let's use this one. Let's do an example. Yeah, so you could, so if you have to factor a polynomial that's larger than a quadratic, you could use long division if there's something that you're trying to extract specifically. I'm not gonna make you do huge polynomials. You could try grouping, right? So when we had more than 4 terms, we were able to group stuff. And so that's usually a pretty good route to go for polynomials with more than 4 terms. I'm not going to give you crazy difficult ones, if that helps. Okay. Let's see here. I'll just have a look at some of these. Right, and so here, the polynomials degree 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. These are all degree 2. So you're okay. I'll stick with, yeah. So these are all, we'll stick to degree 2. I guess this one is degree 3, but it just caught my eye, sorry I missed it. This one's degree 3, but you can pull out a common x squared, it looks like. So x squared times x minus 3. So it's a pretty reasonable factor, I would say. Good. And some of these are already factored, right? Making it kind of nice. Okay. Some of them aren't, right? This one isn't. Right? All right, so if I get you to graph the rational function, r of x is x squared minus 4 over 2x squared plus 2x. Okay. So we can notice some things, right? We've got a degree 2 over a degree 2, right? So, okay, we'll just keep that on the back burner, right? And the first thing we're gonna do is we're gonna factor this thing out. X squared minus 4, you can use a quadratic if you want, or we can say, okay, well, x squared minus 4 over 2x squared plus 2x is going to be x plus 2 times x minus 2. Okay. And then here I can pull out a common 2x. So divided by 2x times x plus 1. Okay. All right, so this is factored as much as I can. So now I can move on to the next step. And what I want you to do is I just want you to just follow these steps, right? So let's deal with the intercepts. The intercepts are where the numerator is 0, right? So the x-intercepts are where the numerator is 0. So step 2, the x-intercept, where x minus 2 times x, oh sorry, x plus 2 times x minus 2, just to keep it the same, is equal to 0. So that's at x equals -2 and x equals +2. You could find that by using the quadratic formula if you wanted to, right? A is 1, B is 0, and C is -4. But these perfect squares, right, we should probably recognize. Or sorry, not perfect squares, difference of squares. The y-intercept is where x equals 0. So like I said, you can plug in 0 for x here if you're really confident in your factoring, but it's no more work to put it into the original, right? And so here, r of 0 is x squared, so 0 squared minus 4 divided by 2x squared plus 2x, 2 times 0 squared plus 2 times 0. So I get what's my holdup? 0 plus 0 doesn't exist. I'm dividing by 0. Actually, I'll make it red. Since we can't divide by 0, there is no y-intercept. And you know what? I'm going to write it so it doesn't take up so much room. Since we can't divide by 0, there is no y-intercept. Okay, so that's okay. So we found our intercepts, our x and our y-intercept. There just happens to be no y-intercept. For the vertical asymptotes, right, so now we're going to figure out how this thing behaves around the zeros of the denominator. So our vertical asymptotes, find the vertical asymptotes by determining the zeros of the denominator, right? So where does the denominator equal 0? And then see if y goes to positive infinity or negative infinity on each side of these things. So here, step 3, the vertical asymptotes is where 2x times x plus 1 is equal to 0. Is where 2x times x plus 1 equals 0. So that's at x equals 0, right? Which we already established, right? There's no y-intercept, so that's okay, because that's an asymptote. And at x equals -1. And x equals -1. Okay, so we've established our vertical asymptotes are at 0 and -1, so I guess I should kind of write them that way. What we can do is we can put them on a number line, just like we were doing before with inequalities, right? So here we have -1 and here we have 0. And because we have this thing factored out, right, we can use the sign test again. So here, right, I'm just going to copy this, paste. So here, oh, and I'll move it down one. The sign on this side of -1, right? So here I've got something like maybe negative 1.1, right? So here you can try something like negative 1.1, and here you can try something like negative 0.9. Here you can try something like negative 0.1, and here you can try something like 0.1. But what you can do is you can use these test values in here to figure out what the overall sign is, because that's going to be, as long as it's positive or negative, which it will be one of the two, obviously, that'll tell you the direction that things are going. So as you're approaching -1 from the left, right? So here we're talking about x approaches -1 from the left. We have, and imagine -1.1 in here plus 2 makes a positive number. And then -1.1 minus 2 makes a negative number, divided by -1.1 times 2 makes a negative number, and -1.1 plus 1 also makes a negative number. So a positive times a negative is a negative, divided by a negative times a negative, which is a positive, makes an overall negative. So y is going to negative infinity. Okay. What I'm going to do is I'm going to divvy this page up here and just kind of keep these two separate by a line as well here. So now do the same thing and figure out the sign of the factored one, which is easier, right? Although if you wanted to, if you prefer, you don't have to use the factored one. You can use the original equation, but then you'd have to plug in the actual number and not just figure out what the sign is. So as we go from x going to -1 from the right, our test point for that, we're using -0.9. So here, -0.9 plus 2 is going to give me a positive number. -0.9 minus 2 is going to give me a negative number, divided by negative number times -0.9 plus 1 is a positive number. Negative divided by negative makes a positive number. So y is going to positive infinity. Talking about 0 here, doing the same thing though, right? So we're plugging in our test value. You can pick any value that's, as long as you're approaching 0 from the left and then 0 from the right, you can use whatever you want. As long as they're close, right? Because we want to know what the behavior is around the asymptote. So that's what's different from the test values that we were picking before, where we could just pick anything in the interval. But here where x is approaching 0 from the left, and over here x is approaching 0 from the right. So if we have -0.1 plus 2, that makes a positive number. -0.1 minus 2 makes a negative number, divided by -0.1 times 2 is a negative number. -0.1 plus 1 makes a positive number. So overall, this is a positive number. So y is going to positive infinity. Last but not least, right? So this is quite a bit of work. X is going to 0 from the right. So let's use 0.1. So 0.1 plus 2 is a positive number. 0.1 minus 2 is a negative number. Probably the easiest one to deal with so far, right? Nice positive number. I guess that's the only difference. 0.1 times 2 is positive, and 0.1 plus 1 is positive. But overall here, we've got a negative divided by a positive, making a negative number. So y is going to negative infinity, right? So at these vertical asymptotes, we're expecting it to go down and then up. and then up, and then down, right? So that's what we're expecting to see here. Okay. What's this going to look like, right? So this is not an asymptote, right? What happens is, okay, here it's going to go up, 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 and then here it's going to go up, up, up. So we suspect that there's some sort of U shape in here, right? Or some sort of parabola in there. In fact, just so it's not confusing, I'm going to delete this now that I've kind of separated them. I just needed to keep them separate. Okay. So what we might suspect is going on here, let's use this one, is that it's going to go down, and here it's going to go up and up and down. So we already know quite a bit about this graph. So those are the vertical asymptotes. Now we deal with the horizontal asymptotes. So step 4, the horizontal asymptotes, we have to look at the degree of the numerator and the degree of the denominator. And so let's see here. I'm gonna just copy this. The horizontal asymptotes. Well, what was our original function here? Copy. Paste. Okay. N in this case is the degree of the numerator, which is 2. M is the degree of the denominator, which is also 2. Okay, so now we have, since n is equal to m, or 2 is equal to 2, then we have a horizontal asymptote at the leading coefficient over the leading coefficient of the numerator and the denominator. So we can say that since n is equal to 2, which is equal to m, there is a horizontal asymptote at y equals 1/2, so 1/2. Right. AN is 1, BM is 2. Or you can just look here. Okay. If they have the same degree. Okay. So what do we have to do? So we know where the horizontal asymptote is. And then we need to figure out how this thing behaves around the horizontal asymptote. Okay. So to sketch this graph, right, next step, sketch the graph. We might need to plot some extra points. Step 5, sketch the graph. Okay. Find more points as needed. Right. It's one of those things we don't like to hear when we're learning stuff. As needed. How am I supposed to know when it's needed? Well, I'll say this: if you graph it in Desmos and you're kind of missing some key aspects, then maybe work backwards like that. Otherwise, this stuff, it can be really hard. I don't want to spend too much time, more than a day on it, because it is sort of important, but at the end of the day, we always have access to graphing calculators, and so it's better to be able to check your work and just kind of use these ideas as quick sketching ideas. Okay, so what do we have here? Well. If I have to draw a sketch, I might as well use my, put a grid here. Hopefully I don't regret it. Sometimes it's hard to move it. Okay. Put my y-axis here, and then I'll put my x-axis kind of here. Why not? So what I'm going to do is, first thing I'm going to do is I'm going to put my my asymptotes on there. So let's start with the asymptotes. And we've got asymptotes at -2 and, or -1 and 0. So here, let's make this -1, and this is 0, of course. So here at -1 and 0, these are my vertical asymptotes. Let's call this 1/2, right? This is 1, 2, 3, 4, etc. So this y equals 1/2 is my vertical asymptote, oh sorry, horizontal asymptote. HA, Hell's Angels. Okay. So we've got this horizontal asymptote. It's hard to see the two vertical asymptotes, which we can call VA. I guess I should define them before I use them. Horizontal asymptote. Which we often call it HA. HA and VA. Okay, so what happens is we need to map. So in general, we figured out the behavior here, right? As x approaches -1 from the left, things are going down. And as x approaches -1 from the right, things are going up. So what we're going to do is this thing is going to go like this. And I'm just doing an initial sketch here, okay? Because we haven't actually established that this is what it looks like, right? But just to get that general behavior of this thing going down as we approach -1 from the left, that's what I'm going to do. So typically what happens is it is pushed up against the horizontal asymptote. And same thing on this side, it's going to be pushed up against the horizontal asymptote. We're going to confirm it by picking some points and some values. But here, it's going to go kind of like this. Okay. Need to confirm this behavior. Okay. But I'm just sketching it right now. Oops. So then we also know that from as we approach -1 from the right and as we approach 0 from the left, right? They're both going up. So what we decided was we probably have some sort of parabolic shape. So what I'm going to do is I'm going to pick a value of x between these 2 points and actually evaluate what's going on here, and maybe pick a couple of points between -1 and 0 to see what the behavior is. And so here, let's see. To determine the behavior, between x equals -1 and x equals 0, we can evaluate the function at different points. And plot them. Okay, so from the side here, because I'm out of time, if x is -0.9, y is 17.72. If it's -0.5, x is 7.5. Or sorry, y is -0.5, -0.45, so approaching that middle or going out again. 7.67, -0.4, just picking different values, 8.0. So it looks like at -0.5, it has a dip down where it's equal to 7.5. So at, let's see here, -0.5 potentially for 5, 6, 7, 7.5. So it actually looks like it goes like this. I made my grid too small. Too large if you think about it. So we've got this behavior. Because I'm out of time, I'll leave it here, but you can confirm by plugging in values of x, right? So let x get really large positive and really large negative. So we'll pick this up next day, but definitely go through and try some of these problems, right? The problems down at the bottom of the page. Do as many of these as you can, okay? All right. Sorry to keep you. Any questions? Okay. Then, oh, I guess have a good weekend. See you on, yeah, Desmos is awesome. Well, have a good weekend. I'll post some more homework for you guys, but it'll be due on the 17th, so you've got time. See ya.